Okay, so let's get into this. Today we are doing a deep dive into, well, one of the most enduring frustrations in the entire history of personal computing. It's a frustration that really defined the mid-1980s, but honestly, it still kind of lingers, doesn't it? Even with all our modern tech.
It absolutely does. We're talking about the great bottleneck, the perennial aching problem of data input.
Exactly. And to get a handle on it, you really have to transport yourself back to 1985. Computing back then, it had these three really distinct phases.
Yeah, that's a great way to put it. You had input, then you had processing, and then you had output. Simple as that.
But the progress across those three areas was just wildly imbalanced.
Staggeringly imbalanced. You look at the processing part, the actual computer, and progress was just enormous. Mind-blowing, really.
We went from, these little 8-bit home micros to incredibly powerful 16-bit machines in just a handful of years. And the output side was accelerating too.
Oh, definitely. You had laser printers starting to come onto the scene. Computer screens were getting faster, sharper. Even the cheap dot matrix printers were getting better all the time.
So processing is flying ahead, output is catching up. But that very first step, getting the information into the machine in the first place,
it felt frozen in time. For the average serious PC user, the small business owner, the writer, the academic, the limiting factor was, and let's be honest, it often still is,
the person,
the speed of a skilled human typist, tapping away on a good old QWERTY keyboard. That was your speed limit.
And there was this feeling in the industry, this kind of resignation, that this was just how it was going to be.
A lot of skepticism, yeah. Nobody really thought human typing speeds were going to suddenly leap forward. And the QWERTY layout, for all its flaws, was so entrenched it wasn't going anywhere.
What about the high-tech solutions, the sci-fi stuff?
Well, you had speech input, which is the big dream, right? But it was.
Yeah.
It was deeply experimental. It needed huge amounts of processing power.
And even then, it couldn't really understand much.
Exactly. The most advanced systems could only handle a tiny vocabulary that you had to pre-program. Totally impractical for, just typing a letter or a report. The human bottleneck was solid.
So this sets up this massive, obvious challenge for the entire industry, this white whale.
Yeah.
Optical Character Recognition, OCR.
The ultimate promise. Just skip the typist, take the piece of paper, feed it into a machine, and get clean digital text out the other side.
But OCR in the mid-'80s was. It was not a consumer technology.
Not even close. It was complex, it needed massive, dedicated computer systems, and it was astronomically expensive.
To really understand that cost, you have to look at who was using it. We're talking governments, right?
Governments, huge banks, massive industrial operations, and we have this fantastic example in the source material that just perfectly illustrates the kind of money involved.
The UK Post Office example. It's incredible.
It really is. The Post Office, a huge national organization, spent millions, not thousands, not hundreds of thousands, millions of pounds.
And what were they trying to do for millions of pounds?
They were just trying to build a reliable industrial-scale system to read postcodes. That's it. One single line of structured, predictable text.
Wow.
And that task showed everyone that a reliable, high-volume OCR system was a multi-million-pound engineering project. It was the absolute high end of expensive, specialized tech.
Which brings us finally to the hero of our story today, the Oberon Omni-Reader. Because Oberon International, they looked at this massive input problem, they saw the millions being spent by these giants, and they made a really unusual, I'd say, brave choice.
They did. They decided to aim for a spot in the market that frankly didn't even exist yet.
What was the promise?
The promise was a practical OCR at a price point that a serious personal computer user could actually afford.
Their whole mission was basically to democratize data entry. And the price. The price is the whole story here, isn't it?
It is the revolutionary hook. The Omni-Reader was launched for £399 plus VAT.
$399. I mean, the reviewers at the time were just floored. They noted it was substantially less than any other OCR device they had ever seen.
And we should put that number in perspective for you. Today, that's roughly £1,320, which, is still a lot. It's an expensive peripheral.
Like a high-end monitor or a really good graphics card today.
Exactly. But compare that to the tens of thousands for an industrial scanner, or the millions the post office was spending. Oberon was trying to sell you a high-speed data entry solution for the price of an add-on, not a whole laboratory.
It was a shortcut. It promised, stop typing. Just buy this box, invest what you'd pay a typist for a few weeks, and start scanning.
That low price was the magnet. But it immediately brings up the big question, the one we need to dig into. If they cut out millions of pounds worth of precision mechanics and optics, where did that cost, that complexity, actually go?
That is the essential trade-off, isn't it?
Yeah.
And it defines this entire product.
They're trying to invent a whole new category, the budget, manually operated OCR, and that forced them into some really, really ingenious compromises.
Okay, let's dive right into those compromises. Section 1. The hardware design. This manual approach, let's unpack this thing.
Well, the first thing is, if you saw it on a desk, you might not even guess it was a computer peripheral.
Really?
It's almost shockingly simple. The source material calls it a miniature drawing board, and that's a perfect description. It's just this flat, angled slab of white plastic.
So it looks more like a drafting tool or something.
Exactly. The whole design is about minimizing expensive moving parts. So the core components are really basic. On the left-hand side, you've got a rail.
Okay.
And running up and down that rail is a sliding plastic rule, a guide. The user lines that up with the line of text they want to read.
And the actual scanner part, the
Yeah.
brains of the operation.
That's what they call the read head. It's this little black box, slightly larger than a box of matches.
Tiny.
All the smarts, the optical sensors, the pattern recognition chips are crammed into that little box. Its job is to look at the text and turn it into the ASCII codes your computer can understand.
So how do you get the paper in there?
You just lay it on the board. An A4 sheet or something smaller, and it's held in place by these two plastic strips that are slightly tacky.
Just to stop it from sliding around.
Exactly. Alignment is everything here, so you need the paper to stay put. The source mentions you could get a longer rule for bigger documents, but the basic unit was fine for standard office paper.
And connectivity. How did it talk to the computer? It's
Yeah.
aimed at the whole PC market, so it had to be flexible.
It was. It plugged into the mains with one of those big, clunky power bricks everyone had back then.
Oh, I remember those.
And then it connected to the computer with a standard serial cable, an RS-232C or RS-423 interface. That meant it could plug into almost anything, an IBM PC, an old CPM machine, even some of the early Apples. It was a very smart choice.
And using a proper two-way serial port like RS-232C is important, isn't it? It's not just dumping data.
It's vital. The machine needs to communicate back and forth. This is why the review specifically warns you not to use a simple printer cable, which might only be wired for one-way traffic.
Okay, so that brings us to the core of the compromise, the manual protocol. The human has to become the machine.
It's a very specific ritual you have to follow, step by step. First, you start at the top of the page. You slide the guide rule down and align it perfectly with the line of text.
Precision is key, I imagine.
Paramount. Then you find the rocker switch on that little read head. You press it down and hold it.
And it's spring-loaded.
Yep, spring-loaded to a neutral position, so you have to keep pressure on it. And while you're holding it down, you have to smoothly, and I mean smoothly, move that little black box across the line of text.
That sounds like the hardest part, trying to maintain a perfectly even speed with your hand.
That's the friction point. But if you did it right, the effect was apparently amazing. The review says words appear on your computer screen as if by magic.
Bypassing the keyboard completely.
Exactly. Then you release the switch, you slide the rule down to the next line, and you do it all over again. Line after line after line.
It's semi-automation. The machine does the hard thinking, the character recognition, but the human provides all the motor control.
And the timing. And you mentioned the rocker switch was dual purpose.
Yes, that little switch is key. Rock it one way and it turns on the scanner. But if you rock it the other way, it acts as a control switch
Before?
for sending commands to the computer. Things like inserting a carriage return, basically hitting the enter key without having to go back to the keyboard. It's a clever bit of design.
It is, but that physical simplicity, as you said, it creates this huge engineering problem that Oberon just had to solve.
Right. How do you compensate for the fact that my hand is going to wobble, it's going to speed up, it's going to slow down?
A conventional OCR would be rendered useless by that. Move too slow, you get garbage. Move too fast, you lose data. It's normally a disaster.
And that takes us straight into Section 2, the clock track. Because this is the absolute heart of their $399 solution. It's how they solved a multi-thousand-pound mechanical problem with a really cheap optical trick.
This is pure genius. It's not about the OCR engine itself, it's about the compensation. As you said, a big, expensive OCR machine solves the speed problem with mechanics.
Right, with precision rollers, belts, stepper motors, all this expensive hardware to move the paper at one single constant speed.
And that mechanical precision is what costs all the money. Oberon couldn't afford any of that, so they had to invent a way to keep the precision electronic, not mechanical.
And their solution, their ingeniously simple method, is something they called the clock track.
Let's break that down, because it's so clever. If you look at that plastic guide roll, the one you slide up and down, there's a pattern printed on it, a series of regular black and white stripes, almost like a little barcode running right along the edge, just below where the text is.
So the read head isn't just looking at the text on the page.
It's looking at two things at the same time. The sensor is split. Part of it is scanning the line of text, trying to figure out the characters, and the other part is simultaneously scanning that perfectly regular pattern on the clock track.
Ah, okay, I get it. So the clock track is like the machine's own private speedometer.
That's a perfect analogy. The machine knows exactly what the clock track pattern is supposed to look like. So by reading how fast those stripes are going by, it can calculate the exact speed your hand is moving at any given millisecond.
So if I slow down halfway through a word,
the machine sees the clock track stripes slowing down, and it instantly adjusts its sampling rate for the text. It knows to expect the character data to be coming in more slowly. It compensates in real time.
it decouples the electronic timing from the clumsy human movement. That is brilliant.
It's how they manage to get acceptable results with the surprisingly wide tolerance for a manual system.
How wide are we talking? What kind of window did the user have to hit?
Anything from about 1 second to 3 seconds to scan a single line of text was considered acceptable.
A threefold variation in speed. That's a huge margin of error.
It had to be. If it was too unforgiving, nobody would be able to use it.
And how did you know if you were going too fast or too slow?
There was a little row of LEDs on the unit, light-emitting diodes. One would light up if you were going too fast, another if you're going too slow. Your goal was just to keep your speed in that sweet spot in the middle where no lights were on.
So it was a constant feedback loop training you to get the right rhythm.
Exactly.
So if you mastered this rhythm, how fast could you theoretically go? What was the top speed?
Well, a bit of arithmetic based on the specs suggests the theoretical maximum was about 160 characters per second.
160. That's insane. A really good typist in the 80s might hit, what, 60 or 80 words per minute? That's maybe 6 or 8 characters per second.
Yeah, we're talking a potential 20-fold increase in raw input speed.
But that's a theoretical number, right?
It's an ideal figure, as the review puts it. You know, like when a printer is rated at 160 CPs, but in real life, you're lucky to get 100 sustained. So a reliable, real-world maximum for the Omni-Reader was probably closer to 100 characters per second.
Still, even 100 CPs is a monumental leap. But what about the other end? Did you have to be really skilled to hit that minimum speed?
Oberon claimed you could scan a line in as little as half a second. But the reviewer, who called himself a fumble-fingered hack, said he found that rather uncertain.
So possible, but not easy.
It suggests you needed a lot of practice and a very steady hand to hit those top speeds consistently.
And that brings us right back to that central tension. You have this brilliant, low-cost engineering of the clock track, but you've just moved the need for precision onto the human hand.
Which is inherently wobbly and gets tired. And that leads us straight into the next big topic, Section 3, the limitations, the feedback, and how it handled the inevitable errors.
Because even with the clock track, a $399 device is going to have its limits.
And it did. It was very sensitive to the quality of the original document. Variations in the typeface, the darkness of the print, a smudge on the page, all of that could throw it off.
So the user needed instant, clear feedback on whether a scan was successful or not. Let's talk about the beeps. The beeping system was absolutely critical. If you scanned a line and everything was fine, the speed was right, the characters were clear, you were rewarded with a single affirmative beep.
That's your green light. Good job, move to the next line.
Exactly. But if the machine had a problem,
Yeah.
maybe your hand was too jerky or it saw a character it just couldn't figure out.
You got the sound of failure.
You got 2 beeps, the double beep. I imagine that sound was the cause of a lot of frustration.
So you get the double beep, the line is bad. What do?
You have 2 choices. You can immediately just try again, rescan the line, try to be smoother, and hope for that single beep.
Wow.
Or you can choose to accept the line, problems and all. Maybe you're in a hurry, you figure you'll fix it later.
And if you accept the bad line, what happens? How does the machine flag its uncertainty?
It puts a special character in place of any symbol it couldn't recognize. The ampersand, the amper symbol.
Ah, so it's leaving a breadcrumb for you. It's saying, I got most of this, but you need to come back and check this specific spot.
It's a practical solution, but it does mean you're always going to have a cleanup phase after you're done scanning.
Were there any specific characters it was known to get wrong?
Yes, the review flags one classic OCR problem as being not unknown, mistaking a capital I for the number 1.
The I-1 confusion. Still a problem today sometimes. And for a human, that's easy to figure out from context.
Of course. But for a machine reading a list of part numbers, it's a catastrophic silent error.
Which brings us to the big question. What was the actual error rate in practice? Speed is great, but not if it's full of mistakes.
The tests found an error rate of about 1 incorrect character for every couple of A4 pages.
One wrong letter every 2 pages or so. Compared to modern tech, that sounds really high.
It does, but this is where the review makes a really fascinating and I think crucial argument. They change the opponent. It's not about the Omni-Reader versus a perfect machine. It's the Omni-Reader versus a human typist.
Okay.
And they argue that for certain very specific types of data, the machine is actually better than a human.
What kind of data?
Data with, and I'm quoting, little or no human meaning. Think about it. Long lists of product codes, strings of account numbers, raw scientific data.
The really boring, mind-numbing stuff.
Exactly. The stuff where a human is guaranteed to make mistakes. Because the machine has 2 huge advantages. First, it doesn't get tired or let its attention drift.
That's a big one.
A human trying to type 1,000 5-digit codes is going to make errors from sheer fatigue and boredom. The machine doesn't. And second, for that specific kind of data, the machine has a higher sustained speed. So over an 8-hour day, it's not just faster, it's potentially more accurate.
So they're making a very targeted case. It's not for writing your novel. It's for inputting the inventory list.
It found its niche where human attention is the weakest link. It's a brilliant bit of positioning.
Okay, that makes a lot of sense. So let's move on to what it could actually read. Section 4, typeface limitations and interfacing. Because this thing couldn't just read any old print, could it?
No, not at all. It was incredibly restrictive. The device had a fixed menu of fonts that it knew, and that list was baked into its ROM, its read-only memory at the factory.
How many fonts was it?
Just 4.
Only 4. What were they?
You had Courier 10-pitch, Courier 12-pitch, Letter Gothic 12, and Prestige Elite 12.
That list tells a story, doesn't it? That is the language of the 1985 professional office.
100%. Those were the standard typefaces you'd get from a high-quality electric typewriter, like an IBM Selectric, or from the expensive daisy wheel printers that businesses use.
So your document came from a corporate environment, you were probably okay.
Right. But, and this is a huge but, especially for the market they were supposedly targeting.
Let me guess. What about the most common type of printer for personal computer users?
Exactly. The source is crystal clear. Dot matrix printing is off the menu at the moment.
Wait a minute. That's the great irony of the whole thing. The low-cost OCR device for the masses couldn't read printouts from the low-cost printers that the masses actually owned.
It's a massive disconnect. The person most likely to buy a $399 dock scanner is the person who could only afford an Epson or an Okidata dot matrix printer. But the output from those printers, with the visible dots and less consistent shapes, was just too fuzzy and unreliable for the Omni-Reader's simple pattern matching.
So its main use was for scanning documents that were already lying around. Things generated by expensive corporate machines, not new stuff you printed yourself.
That seems to be the case. It really limited its utility. They did have a plan to fix this, though. A future upgrade they called Learn Mode.
Ah, so you could teach it new fonts. How would that have worked?
The idea was you could train it on one additional typeface. You'd have to scan samples of the font over and over again, and the machine would build a custom recognition profile for it.
And where did it store this new font profile? Not in the ROM, surely.
No, it would be stored in the machine's RAM, its random access memory. And this points to the hardware constraints of the time. RAM was expensive, and more importantly, it was volatile.
Meaning if you turn the power off, it's gone.
Poof, gone. So the catch was, you would have had to save your custom font profile to a file on your computer's floppy disk before you shut down the Omni-Reader. Every time you wanted to use it, you'd have to load it back in. It was a clumsy workaround.
A very 1980s solution. Okay, let's talk about hooking it up. Interfacing? Was it a pain to get it working?
By 1985 standards, it was apparently fairly straightforward, which is high praise. We already mentioned it needed that proper two-way RS-232 cable.
A modem cable, not the printer cable.
Right. Thankfully, a standard IBM modem cable worked just fine with the IBM PC, which covered a huge chunk of the market.
And you could set the speed, the baud rate?
Yep, using a little block of physical switches on the unit, called DIP switches. You can set it for anything from a crawl at 300 baud all the way up to a pretty zippy 9600 baud.
9600 was flying for a serial port back then.
It really was. The review says the IBM setup worked quite happily at 9600, which meant the characters would just flow onto the screen almost instantly as you scanned them.
And what else did those little switches control?
There was a whole other bank of them for setting other options. You could tell it whether to expect a 10-pitch or 12-pitch font, which was critical for the optics to judge the spacing correctly.
And some very region-specific stuff, too, I saw.
Oh, yeah. You could flip a switch to tell it whether to expect a pound sign or a hash sign. It really shows you how unstandardized things still were back then. You could also set the handshaking protocol to make sure the computer and scanner were communicating reliably.
So a lot of physical configuration before you even started.
It was a very hands-on device in every sense of the word.
Okay, so we've got it hooked up. We know what it can and can't read. Let's get to Section 5, Applications and Market Position. Once you scan the data, what do you actually do with it?
Well, there were two main ways to use it. The simplest way didn't require any special software at all.
How did that work?
You could just use your computer's operating system or write a tiny basic program to open a file and tell it to listen to the serial port. The text from the Omni-Reader would just get dumped straight into that file. Raw text.
Useful for archiving, I guess.
Yeah.
But the real power came from getting it into your actual programs.
Yeah.
Your word processor, your spreadsheet.
That's where it became a true productivity tool. But for that, you needed special interfacing software, which was available for big platforms like the IBM PC.
And what did this software do?
Its job was incredibly clever. It would merge the data stream coming from your keyboard with the data stream coming from the Omni-Reader's serial port.
So trick the application.
It tricked the application completely. As far as your word processor, say WordStar, was concerned, it didn't know the difference. It just thought you were a ridiculously fast typist. It saw one seamless stream of characters coming in.
That's the key, isn't it?
Yeah.
It makes it universal. You don't need a special version of WordStar.
Not at all. And it opened up some great use cases. You could be in WordStar and just start scanning continuous text from a report. The text flows in, and WordStar handles all the word wrap and formatting, just like normal.
And because the keyboard's still active, you can pause, type a command to save the file, and then go right back to scanning.
It's a seamless integration.
But you still needed a way to put in things like paragraph breaks.
You did. You could do it manually by flicking that rocker switch on the read head the other way. That would send a carriage return character. Or you could set the machine to do it automatically after every successful scan, which was great for lists or tables.
Now, the article mentions a use case that must have made a lot of people's ears perk up back then, entering program source code from magazines.
The Holy Grail. For anyone who lived through that era, you remember spending days, literally days, typing in pages and pages of basic or assembly code from the back of a magazine.
The idea of just scanning it in minutes, it must have seemed like a miracle.
It did. But we have to really question the viability of that, given the error rate we talked about.
That one mistake every couple of pages.
It's a deal breaker for code. In a normal text document, if it swaps an I for a 1, you'll spot it instantly. In a line of code, a single wrong character, a colon instead of a semicolon, a quote mark missed.
The whole program just won't run, and you have no idea why.
And you could spend hours, maybe even a full day, hunting for that one tiny error the scanner introduced. The time you save scanning would be completely wiped out by the debugging.
So the risk was just too high? The promise was bigger than the reality for that specific task?
It really was. Which brings us back, once again, to the ideal application for this thing, where it really truly shone.
Numeric data.
All day long. For those lists of codes, numbers, anything non-contextual, the Omni-Reader had a killer feature, numeric data mode.
So how did that improve the accuracy so much?
It just massively simplifies the machine's job. In normal mode, when it sees a vertical line, it has to guess, is that a lowercase l and uppercase I, the number 1? But if you switch it to numeric data mode, you're telling it to only expect numbers from 0 to 9 and a few special symbols like decimal points.
It narrows the universe of possible characters, so the chance of it making a wrong guess goes way down.
Way, way down. It gives the machine much higher confidence. And this feature was described as a boon for some applications. If your job involved keying in stacks of printed financial data, this thing was genuinely revolutionary.
Before we wrap up, it's worth mentioning one last thing the reviews praised, which is a bit unexpected.
The documentation.
The documentation. For a complex piece of kit, that's huge.
They did a good job. It came in 2 parts. A general user guide and a more technical guide for the interfacing side of things. All the info was there.
But the best part was the troubleshooting guide.
Yes. They highlighted that it was a comprehensive troubleshooting guide, and this was a direct shot at the rest of the computer industry at the time.
What was the common problem?
Most manuals at the time would just drone repetitively, consult your dealer whenever anything went wrong. It was useless. Oberon's guide actually told you what to do if things didn't work. It showed they were thinking about the user experience.
It really underscores that they were serious about putting a professional tool into the hands of a non-expert user.
It added a lot of perceived value.
All right, let's pull it all together. Final section. Conclusion and legacy. What was the final verdict on the Omni-Reader?
Well, the consensus was that this was not intended as a replacement for the heavy-duty OCRs. Anyone with a big, expensive industrial scanner would have just sneered at it.
The manual operation, the limited font.
Exactly, but that completely misses the point of what Oberon was doing. They weren't competing with those guys. They were trying to search out a new group of users.
A group that could never, ever have justified spending tens of thousands on an OCR machine.
And this is a classic story in the history of the PC. The article says that history is littered with examples of companies who did this. They invent something useful at a price that opens it up to a whole new audience, and they end up creating their own market from scratch.
The value proposition really came down to a simple calculation, didn't it?
It did. A skilled human typist was still better in many ways. They could read handwriting, they could handle poor quality copies, but the Omni-Reader was so cheap it was worth a try anyway.
And the economics were compelling. The reviewer figured you could save £400 worth of a typist's salary pretty quickly.
And since the machine cost $399, your return on investment could be just a matter of weeks if you had a big backlog of paper to digitize.
That's the argument that would have won over a small business owner right there.
Yeah.
But obviously we don't see these on every desk today. What happened to it?
It was a brilliant solution to a temporary problem. Technology just moved on. The cost of true flatbed scanners started to fall, and then you got the introduction of handheld wands that you dragged over the text, which were a bit more flexible.
The Omni-Reader's very rigid, controlled method was its strength and its weakness.
And that core requirement that the human operator had to be the precision transport system was always the biggest point of friction. It required focus, it required practice. The human was the most inconsistent part of the system.
Which leads us to our final provocative thought for today. The Omni-Reader got to its amazing price point by outsourcing the most expensive part of the machine, the mechanics, onto the user.
The user had to become the motor, the precision engine.
So the ROI was obvious in pounds, but the hidden cost was the mental energy, the practice, the sheer attention required from the human.
Oberon showed us that when you create low-cost automation, you're often not eliminating complexity, you're just transferring it.
You have this brilliant device, a breakthrough in low-cost engineering, and yet its biggest limitation wasn't the chips or the optics. It was the fumble-fingered hack holding the read head. So it really makes you ask a question that's still relevant today, doesn't it? When we design tools to save time and effort, where's the line between true automation and just shifting the burden of precision back onto the person we're trying to help?
The Omni-Reader is this fantastic case study of genius problem-solving under tight constraints. But it's also a monument to just how hard it is to get a human to act like a machine.
And that is our deep dive on the Oberon Omni-Reader, the $399.9 answer to the great input bottleneck of 1985. Now, if you'll excuse me, I'm going to go try and move my mouse across the screen at a perfectly constant speed, see if I get a single beep. Good luck with that.
Yeah. We'll see you next time.